Assalamu alaikum students. Today we will discuss the chromatic dispersion and polarization mode dispersion in single mode fiber. The data rate or the bit rate that we can achieve at the other side of the optical fiber, that depends upon the dispersion that we are undergoing. So let's start, and first of all we will discuss the chromatic dispersion. We have already discussed the modal dispersion, which was related to the multi-mode fiber. As we have already discussed that single mode fiber does not have any other mode, it means that it has only one mode, so the possibility of intermodal dispersion minimizes. But we do know that if the frequency is increased or the wavelength is decreased, then another mode can emerge in a single mode fiber also. We restrict the number of modes to one by just restraining the size of the physical size of the core and the physical size of the core and the wavelength, because we are using wavelength at least more than 1300 nanometers. If we go lower than that, then newer modes would emerge, and that is not required, and that is not feasible in a single mode fiber. So let's start. You can refer to the presentation slides of lecture number 10 that I have already shared with you. These have been developed based on chapter number 5 of our textbook, which is Fiber Optic Communication Technologies by Jaffer and Lovell. So let's see. We do not have a single mode, we do not have a modal dispersion in a single mode fiber, but we do have chromatic dispersion as well as polarization mode dispersion. Polarization mode dispersion, or PMD, is a new word, and we will see what does that mean and how does it contribute to the total dispersion in a single mode fiber. First of all, there are no intermodal dispersions in single mode fiber. Lower dispersion means higher bandwidth. That's why we are able to send larger bandwidths, larger data rates over longer distances while we are using single mode fiber. But that is not possible with a multi-mode fiber. The multi-mode fiber can carry higher data rates, but to a smaller distance. So within 500 to 1 kilometer range, that is possible. It is quite possible, and it is quite feasible to use multi-mode fiber, but the single mode fiber is normally used for longer distances. We prefer in-building and within campus communication over multi-mode fiber, because the cost of the sources and the receiver, which is the LED, which is the source, and its receiver, that is quite low as compared to the laser diodes that we need to use in case of single mode fiber. So in single mode fiber, there are two types of dispersions. Number one, chromatic dispersion, and number two, polarization mode dispersion. So as you know, the chromatic dispersion means chromatic comes from the word chroma, which means colors, and the colors mean different wavelengths in in a material. Basically, there are two basic sources of chromatic dispersion. Number one is the material dispersion, and the second one is the waveguide dispersion. As we know that there is no such source in the world, even if it is a laser source, that has that does not have a spectral width. There would always be a spectral width attached to a certain source. For example, a laser diode can have a very small spectral width, but it does have some spectral width. How much would it be? 2 nanometers, 1 nanometer, or even less. But it is not possible to have a completely single wavelength produced by a laser diode. So we do have a limitation that we have a certain spectral width that we have to cater for. So and this particular situation is basically catered and called the material dispersion, and it is due to the wavelength dependence of silica. As different wavelengths or a range of wavelengths travel through silica, which is basically the core, what happens is that the lower wavelengths they take longer to reach the destination, while the larger wavelengths reach the destination earlier. Reason being the fact that their velocity is more, and this can easily be understood by the equation c is equal to nu lambda, where c is the speed of light. And let me remind you that the speed of light in silica is not 3 into 10 to the power 8 meters per second. It is rather approximately 2 into 10 to the power 8 meters per second. Reason being the fact that here the medium is not air or space. It is the core, which has a certain refractive index, which is almost close to 1.5. So when we divide 3 into 10 to the power 8 by 1.5, we get 2 into 10 to the power 8 meters per second. So since different wavelengths travel in the in one particular optical fiber, and it is generated by the laser diode, the light pulse contains different wavelengths, because light sources radiate light in light of a finite spectral width. And what is spectral width? The range of frequencies or wavelengths emitted by a transmitter and surrounding the central frequency or wavelength at a power level equal to half the maximum power level. What does that mean? You can see in this diagram that the intensity of the light produced by the source or the laser diode is drawn as with respect to the wavelength. The central wavelength is called lambda naught, as shown over here. At this wavelength, the intensity is the maximum. As we move forward or in the reverse direction, that is having more wavelength or the lesser wavelengths, the intensity reduces until the time comes that when it comes to 0.5 times the maximum. And what is the wavelength over here? It would be lambda plus delta lambda by 2. And what would be the wavelength if we move in the reverse direction or towards the lower wavelength? A time would come when the intensity would 0.5 times or half of the maximum intensity. We would note the wavelength over here. It would be lambda naught minus delta lambda by 2. What is delta lambda? Delta lambda is the spectral width of this particular source. So it comes from here till here, right? So in a laser diode, normally the delta lambda is approximately 1 nanometer or 2 nanometers or even less than 1 nanometers. But in LEDs, it might have different values ranging between 50 nanometers to 140 nanometers. I would refer to figure number 5.8 of our book, which is Fiber Optic Communication Technologies by D. Jaffer and Lovell. Also, you can find this figure in the presentation that I've shared with you, this presentation on lecture number 10. So it shows clearly that when such a light travels through the optical fiber, it goes through the core of the fiber. What happens is that a range of frequencies pass through it, starting from lambda naught minus delta lambda by 2 to lambda naught plus delta lambda by 2. Lambda naught plus delta lambda by 2 is the highest wavelength, and it reaches the destination earliest. And lambda naught minus delta lambda by 2 is the smallest wavelength, and it reaches the destination the latest. So there is a distance, or there is a difference between the time of arrival of this wavelength and this wavelength. This difference creates the dispersion. Lambda naught is considered to be the reference point. So the pulse lambda naught plus delta lambda by 2 arrives before this reference wavelength, while lambda naught minus delta lambda by 2 arrives at the destination later than this reference wavelength lambda naught. Now, the material dispersion in both the single mode fiber and the multi-mode fiber is the same. If we want to calculate the value of this material dispersion, we can have the formula delta T material is equal to D material delta lambda into L, where delta lambda is found out in picoseconds, right? And L is given in kilometers. Delta lambda is given in nanometers, right? So what is D material? This is the material dispersion parameter. D material is the material dispersion parameter. Delta lambda is the spectral width of the source. Now we move on to our next type of dispersion that contributes towards the chromatic dispersion. First of all, we had the material dispersion. Now it is the waveguide dispersion. Waveguide dispersion is caused when light is guided by a structure like an optical fiber. In single mode fiber, major portion of light travels in core and some in cladding. What is the reason behind that? The reason behind that is that the light beam or the front of the light beam does not have strict boundaries. It follows the Gaussian equation, and we have already discussed in our last lecture that it is basically it brings up the mode field diameter, and we have already learned that the mode field diameter is a bit larger than the physical core diameter. For example, in some cases, if the core physical diameter is 8.3 nanometers, then the mode field diameter might be 9.3 micrometers in many cases. In such a case, the whole light would not travel in the core. Approximately 20% of the light will have to travel through the cladding. Now what happens is that the cladding has lower refractive index, which causes a larger speed of light. Simply, we can come to this conclusion from the formula that the speed of light in a certain medium is equal to the speed of light in free space divided by the refractive index of that medium. That is, V is equal to C over N. If this light travels in the core, for example, if the core has a refractive index of 1.48, it would give a certain value of velocity over here. If we check what is the speed of this particular light in the cladding, while we are saying that 20% of the light is traveling through the cladding, then the value of V would be higher because N would be smaller, because the refractive index of cladding is smaller as compared to the refractive index of the core. Both portions of the pulse travel at different speed due to the relation of light speed with the refractive index. So the pulse received at output is wider than at the input, because some of the portion of that particular pulse reaches via the cladding and it reaches first, while the portion that comes from the cladding, it reaches later, and it causes the extension or the widening of the pulse. Now, how can we find that this particular waveguide dispersion? The formula is quite similar to the one that we have found out for the material dispersion. The difference is this dispersion parameter. This dispersion parameter is due to the waveguide dispersion. You can compare these two uh, dispersion parameters from this diagram. This is shown in figure number 5.9 in the book, and slide number 14 in the presentation slides. I would like you to open the book, or at least the presentation, and go to slide number 14. You can see that the material dispersion parameter, it starts, if we plot it against a range of wavelengths starting from 1100 to 1600 nanometers. The waveguide dispersion parameter starts from a negative value, approximately -25, and it goes on increasing. At approximately 1300 nanometers, it crosses the zero line, and then it goes into the positive domain. While you can see the curve of the waveguide dispersion, it remains in the negative domain. It does not go into the positive domain. The total dispersion due to waveguide and material reasoning, or the material dispersion and the resultant of the waveguide dispersion and material dispersion can be had by just adding these two up. When we add both of them, we would see that the resultant curve would cross the zero line at 1310 nanometers, which we have already learned that that is the wavelength of minimum dispersion. That is, the minima of dispersion occurs at 1310 nanometers. That is the reason. That is the particular reason for that. Let me remind you that the wavelength of attenuation minima is at 1550 nanometers for a normal step index single mode fiber. By improving some profiles, the index profiles of the fiber, we can shift the wavelength at which we get a minima for dispersion, and that is what is exactly done in case of dispersion shifted fibers. What we do is that we shift the dispersion minima from 1310 nanometers to 1550 nanometers, so that it coincides with the attenuation minima. So we get a very good ideal optical fiber with minimum attenuation and dispersion at one particular wavelength, which is 1550 nanometers. We'll see to it in further studies. Now, let me take you to the figure number 5.10 of the book, and which is the slide number 13 on the presentation slides of this lecture number 10. You can see that the wave is moving through the core, while a certain part of the wave is also passing through the cladding. Approximately 20% of the intensity of this light is going through the cladding. What happens is that the light passing through the cladding reaches the destination earlier as compared to that passing through the core. So what happens is that the pulse at the receiver extends or widens. This widened